Welcome. We'll be discussing using and testing Triacs and Triac-based optocouplers. I'm Lewis Laughlin. My website will be at www.llaughlin.com. Excuse me. We'll be discussing a number of topics here on Triacs. We will be looking at spec sheets, how to read them, and various circuits. This is an updated version of a test circuit that I had built earlier. It demonstrates a number of things. What I ran into some years ago when I was in the welder repair industry is we had a couple of boards that had blown Triacs. Triacs were being used with optocouplers on these boards as solid-state relays to switch on various functions in the welders. Let's see how this works and why it works the way it does. This is 24 volts AC. I like to keep these voltages low. This is a 24 volt lamp. You'll see that here's the Triac and how it's wired. Your trigger voltage always on a Triac must originate with the T2 terminal, not T1. Here is an equivalent SCR. You can use this for SCRs too, and I'll explain how. Alright, to run the test, run this pot all the way down counterclockwise, assuming it goes up towards the voltage clockwise. Press switch 2. Adjust the pot until it's about, the light bulb is something like 80% full brightness. Now, if it stays on all the time or you can't adjust it, you either got a wiring problem or you got a blown Triac. Try another Triac. Assuming your Triac is good, adjust the 10K pot for about 80% brightness. Release S2. Press S1. You should see half the brightness. This test Triac is sort of like two back-to-back SCRs that we'll see in the next slide. You're testing each side of the Triac for two things: that both are working and that they are working the same way. Press S1, the bulb should be about half brightness. Release S1. Press S3. Should be the same. Brightness again. That means both sides are balanced. If you press S1 and S3 together, it should be back to 80% brightness. Release both and press S2, and it should be the same brightness as S1 and S3 pressed together. The troubleshooting problem I ran into years ago involved some defective new replacement Triacs. We had a board. As I remember, it had 3 Triacs on it. 2 were obviously blown apart. 1 still looked okay. The technician replaced all 3, checked all the other parts, and he couldn't figure out what the problem was. It just didn't work correctly. I had a test set up similar to this, so I removed the 3 Triacs, and did this test. I checked one side I set the Triac fully on, set up one of them. This would let me compare the 2 sides of the Triac and the 3 Triacs themselves, and even with the new replacements that we had in a box. So what had happened, one of the Triacs that they had replaced, if you press S1 and S3, they were not conducting the same way. Thus, when it was triggered, it wasn't working correctly. The other problem was these were substitute Triacs. I had some originals, and I thought I would compare them. 2 problems we ran into. One of the new Triacs was just flat out defective. I don't know where they got these things. Was flat out defective because it did turn on both sides, but not equally. You would press, say, the S3 at the time, it would be 40%, and the other one would be 20%. In addition, when I compared the gate trigger with the originals versus the replacements were not near as sensitive as the originals. We're going to discuss why those things happen as we move along. Let's look at this circuit a bit. What I've done here is wire, just for demonstration purposes, there's 24 volts AC. I wired two SCRs, anode, cathode. So when I pressed S3 or S2, one or the other would conduct just like it did before. If I press S3, okay, the light bulb would light up, so-so. If I pressed SW2, the light bulb would light up, so-so. If you press both, it lights up fully. So you can look at the internals in a Triac as if it was some form of back-to-back SCRs. I have web pages on this that explain that in detail and how to trigger them off and on. Alright, let's drop back to a project that I put out a couple of years ago, and we're going to update it. This is my Arduino power control. It will control the brightness through this control or through programming the brightness of a 120 volt lamp through this Triac. This is an MOC 3010 Triac output optocoupler. It is wired in, the output is wired in series. Again, we're coming from M2 through a current limiting resistor back to the gate. You flip the switch, and you use the pot here to adjust the brightness of the bulb. How does this work? This is a zero crossing detector. I have several of those. The links will be at laughlin.com. When you go to it, it'll be right there on the page where you can go look at the individual pages. It puts out pulses. What kind of pulses are zero crossing pulses? Look closely at this off my oscilloscope. You notice that each time it crosses zero, the point where it goes from positive to negative or negative to positive, you notice I get a pulse. How this system works, this is called phase control. I get many questions about pulse width modulation. This is not PWM. It is nothing like it. This is phase control. So what this does, and if just leave me a request, I'll cover the full explanation of this again and update it, is it looks for a pulse. It trips the interrupt in the Arduino. The Arduino reads the pot, and it calculates from the pot how long I delay. The longer that I delay, say it, let's go right here. Okay, it gets a trigger pulse off the zero crossing detector. If I wait, okay, and this is 180 degrees. If it's 60 hertz, I think it's about 8.7 milliseconds from here to here. The longer I delay sending the turn-on pulse to the MOC 3010 optocoupler, that means the less power is out. So if I have 180 degrees, if I trip it on at 150 over here, the bulb's not going to light up much. If I trip it here at, say, 10 degrees, the bulb will be fully bright because it's on enough, long enough to give you full output. And it will do this on every positive and negative pulse. So, to reiterate, this is a zero crossing detector. It gives me these timing pulses, and this will be a 120 hertz pulse, because it might be 60 cycles, but it crosses zero 120 times a second, or 120 hertz. It reads the pulse, calculates a delay, reads the pulse through the interrupt, calculates a delay, turns on the MOC 3010, fires the triac at the phase angle from the zero crossing pulse from 0 to 180, which is 8.7 something milliseconds. All right, let's continue on. All right, here's another use of a triac. This is a basic lamp dimmer. This is a diac. We will be looking at diacs in this too. How this works. And by the way, this is a bilateral switch. It conducts either way. A diac is not a diode. It is a bidirectional Schottky sort of thing. It also conducts in both directions. It will turn on. What happens is, okay, you got your positive going pulse. Doesn't matter if it's negative or positive. This will trip on at about 32, the ones that I use trip on at 32 volts. So the capacitor's charge time up to 32 volts depends on the combination of the pot setting and the size of the cap. So when the cap charges up to 32 volts, you will get an avalanche effect. This will break down and give you a clean pulse into the gate cathode circuit, anode cathode gate. As again, the trip voltage for the gate is still derived from T2, which is up here. All right, let's see what's next. All right, here is examples of optocouplers. This is also, we're going to go into the spec sheets in a moment. This has a gallium arsenide light emitting diode. It's in the infrared region, and this is a silicon. It looks like a diac, but it's a photo triac, I believe. It is a photo triac. Light hits the connection that would have been the gate. This turns on. Let's move over to the schematic, to the spec sheets and see what we have there. All right, let's look at the two different optocouplers that I use in these circuits. The first ones would be the MOC 3010 through MOC 3012. There's some differences, but they work basically the same. Let's look at what we need to know in our spec sheet. Okay, these are random phase optoisolators with Triac driver output. It consists of a gallium arsenide infrared emitting diode coupled to a silicon bilateral switch. These are designed for Triac triggering. That's what they do. It is possible to use a low power lamp, such as a low power 24 volt lamp, but they're not made to drive a load. They're made to trip on and off Triacs, or you can use them in SCRs. I'll show you some tricks on that. Some of the uses of these, let's move down a bit. You can use them as solenoid valve controls, lamp ballast. You can interface microprocessors. That's what I did with the Arduino. You can use them as motor controls, static AC power switch, solid state relays, or incandescent lamp dimmers, and so forth. All right. It consists of a 6-pin package. Most of them do. Here's your diode. It generally... Here's the specs on the infrared emitting diode. It's rated about 3 volts. Its maximum forward current is about 60 milliamps. It works fine at 10 milliamps. And it has a power dissipation of 100 milliwatts. So yeah, I've used them plenty of times at 10 milliamps. That's all you need. That's from my test. The output, of course, is a photo Triac that's connected from pin 4 and 6. It just switches on. It is bidirectional. Doesn't matter how you hook it up. All right. You can look at some of the other. These are rated for This one's rated for 250 volts, which means you cannot use it on 240. 40 for that. I think they have some of them that are rated for, yeah, this one's rated for 250 volts. You can use a very short pulse and go up to an amp with it, but continuous, no. Let's see. That's the diode, the output driver. It is 250 volts. I would rate it at about 300 milliwatts. Let's see what we got further down. Okay, here's the LED. Leakage current. Forward voltage at 10 milliamps is going to be 1.5 volts. Sounds about right. Output detector. So forth. Here's your differences in the different types. Main terminal voltage. Okay, that's the trigger. That's the LED trigger current. And so forth. And you can go through all that. Let's move on down to some other things. Here are some test circuits. These particular ones are used for 120 volts AC. Let's look at this circuit. This is going to connect between 6 and 4. It could have been 4 and 6. It doesn't matter. Here is your load. Here is your line. You connect this to VCC. Connect this to your Arduino. I usually don't fool with that. I connect the Arduino directly to it. I put a resistor to ground and connect the Arduino output high to pin 1. Nonetheless, here is your load. Here's your 120, and this is your this is by the specs. It's a 180 ohm current limiting resistor for the gate of the Triac. Let's look at some differences because I've been asked this before. This is for a standard Triac. Now, when you're dealing with inductive loads, when you're switching in inductive loads like motors or solenoids, you're going to produce spikes, static, and noise. That can cause false triggering on the Triac gate. So what you've got here, also this is a sensitive gate Triac. We'll discuss the difference between sensitive and non-sensitive gate Triacs that gave us trouble with those boards that I discussed earlier. This time we sort of got a voltage divider in it to cut down the current, since this is a sensitive Triac. This is also a capacitor to help keep noise out of the system. Let's look at the other one down here. Okay, this is a non-sensitive gate Triac. You notice that the 2.4K resistor has been changed to 1.2, and the capacitor is a little bigger, so that keeps the noise sensitivity out. And that's all there is to these. See if there's anything else. Nope. And so again, resistive load, light bulb or something, straightforward connection. If you're going to do things like inductive loads, motors, solenoids, or whatever, you've got to put the extra resistor and caps in there that helps stabilize and protect the Triac gate. For a non-sensitive Triac with a inductive load, you're using a smaller resistor, a little different capacitor, and so forth. Alright, before we leave this spec sheet, once again, this is just a Triac output. No zero crossing circuitry or anything like that. That is what you want to use with this circuit. You can't use one with zero crossing circuitry. Now, also note that this one's designed for 120 volts. If you need to use 220 or 240, you can use the MOC 3020 through 23. The electrical connections are identical. They work the same way, but these are designed for 220 volts AC instead of a 250 volt breakdown for the 3010s. This one is 400 volts. Let's just make sure. Or you can use this one too on 120 or 240. Depends on what you have. I'd probably go with this one. Here it is. 400 volts. Your diode is similar. 50 milliamps. Yeah, most of it is really the same. Other than this one is rated for 400 volts. Now, let's discuss a third type of Triac optocoupler. This is the 30, 31, 32, 30 series, 4 and 40s. These are the 30, 31s are 250 volts. The 30, 41s are 400 volts. These contain the these have 0 crossing circuits in them. This is what it looks like internally. Again, it hooks up like this is pretty standard. 4 and 6 are your output terminals. Same deal with the gallium arsenide LED. The only difference is with this, and it's fixed. When you turn on the LED, you trigger the gate circuit in the internal photo Triac, but it holds off firing until you get a zero, until you cross 0 on the AC sine wave. That also means that you cannot use it for, it's fixed. You turn on the LED, this will turn on a few degrees past 0, and turn it on. The 180 degree cycle will be fully turned on. This cannot be phase controlled. It's no good for that. Let's go down and look at some more circuits related to this. Again, it's the these are the ones you want to use for if you need a 0 crossing detector and you're just turning on a light or turning on a motor and you don't want to do phase control for speed or dimming or anything like that. Let's move on down. It's got circuit examples we all may find interesting. Move on down. Device under test. Here we go. Let me see what's in my plate. I blew these up, so well, I can still blow it up. All right, let's look at this circuit here. Looks pretty much like the other one. Everybody has also asked me on these circuits, where did I get the values for the snubbers? Right on the spec sheet. This is from the manufacturer. This is for highly inductive loads. This prevents false triggering of the gate and other problems. Okay. The 330 ohm, let's see, for highly inductive loads, you might want to change the 39 ohm to 360 ohms according to the spec sheet. And this is a 240 volt AC connection. Let's go on over here. It's pretty much identical for, yeah, it looks identical for 115. That's a 180 and a 1K. For 240, it's a 360 and a 330. So there's differences in these gate resistors, and this has a snubber. This will also use a snubber if you're using an inductive load. There's one more circuit down further, I think. Let's go back a bit. Ah, yes. One of my favorites. Now, I've discussed this. I have web pages on this. Remember, we were discussing the idea of using two SCRs back to back that they could mimic a Triac. This circuit here is that. This is the manufacturer's ratings. R1 and R2, I think, are optional. Let's see what they are. Yeah. Let's shrink that down a little bit. All right. There's your circuit. It uses two diodes, two gate resistors, and these resistors and diodes, note the polarity of the diodes. They're 1N 4001. Probably 400 volt diodes will work just fine. Suggested method of firing two back-to-back SCRs with a Fairchild Triac driver. Diodes are 1N 4001. Resistors R1 and R2 are optional, 330 ohms. When I wired mine up, I put in the resistors, and it seemed to work fine as far as I could tell. Note, again, the opto isolator should not be used to drive a load directly. Now, what can we do here? This has a problem, is that this particular MOC 3040 series optocouplers have zero crossing circuits. Thus, you can't use them for things like this Arduino phase control circuit. But the answer is fairly simple to fix that problem. Use this circuit. Let's go down and look at it again. And you can download these spec sheets. Use this exact same circuit and use an MOC 3010, or if you're using it at 240, go over to the MOC 3020. The 3020s and the 3010s do not have internal zero crossing circuits. Yes, let's look a little bit more at our MOC 3020s. These are the higher voltage, non-zero crossing circuits. You can see this is pretty much standard. They hook up much the same. You got the 180 ohm current limiting resistor for the gate. If you're going to, in this case, 220 volts AC, here is your 180, 2.4K, and a 0.1, just like the other ones we saw. And this is particularly for the non-sensitive gate versus sensitive gate. We saw something similar over here. They were talking about sensitive and non-sensitive gate devices. What do they mean by sensitive and non-sensitive gates? Let's look at several spec sheets on Triacs. First, let's look at the BT136 Triac. It is in a TO220 case. Here's your pin connections. There's your symbol. It is rated at 6 amps at 600 volts. Let's look down at our whatever. RMS on state, 6 amps. You can go through and read these yourselves. You can pulse this thing up to a pulse width of 20 milliseconds or 16 milliseconds, up to 25 or 27 amps. You can have a peak gate current of 2 amps, but you're talking about a millisecond pulse at the most. You don't drive it like that. Okay, here's your 600 volts, peak off current, and so forth. The one I'm looking for is okay, gate trigger current. The gate trigger current for this particular series is a maximum of 3 milliamps. That's not super sensitive, but that's not bad either. Let's look at another. Let's compare this to another Triac. This is the BT137-600. It is, again, of course, 600 volts at 8 amps. Let's keep looking. Okay, this is another thing you need to do is holding current. You have to keep these things will switch on and off because your AC sine wave is going to 0. So let's go on down here. What am I looking for? Okay, repetitive state. Yeah, you can do 8 amps. I'm looking for the gate trigger. That would be, let's see, peak gate current again, and this one is 2 amps, and that's in milliseconds. Alright, let's look further down. Alright, you silly thing. Where did you put it? Okay, this should be, okay, here it is. Ooh, this is pretty bad. This is, the thing you're looking for with gate triggering is IGT. This thing could be up to 10 milliamps, so that's considerably more than our first one, which was sitting around 3 milliamps. Let's look at another one. So obviously, the first one here is more sensitive than this one. Let's look at another. Okay, this is a BT139. 600 volts, 16 amps. And so that's a fairly high-powered one. Let's see IGT. This is ridiculous. You'll notice that the higher power that they carry, generally it's going to have a higher gate trigger current. This can be up to 30 milliamps for a trigger current. Your really small, really sensitive ones can be in the microamps. So these are heavy-duty Triacs. This one's 30 milliamps gate trigger. This one can be 10 milliamps. Okay. And this one is 3 milliamps. So you gotta notice the diff. When you're replacing a Triac, look it up on the spec sheet and note the gate trigger current, because they're different. Really sensitive gate Triacs, I've got some SCRs that'll trigger on at 300 microamps. So be aware of these gate trigger currents. All right, let's return to our SCR setup. As we said earlier, this optocoupler has 0 crossing circuitry. You can't use it with the Arduino. Instead, use the 3020 instead. If you're going to use phase control through a microcontroller, use the 3020 or 3023. Okay, let's take a look at the DB3 Triac. The Triac is this here. There's different symbols for it. looks just like it looks like a diode generally, or it can be a surface mount device. This one has a 32 volt trigger circuit. This is for 32 to 40 volts. My measurements using these, and I've got some of these, mine came from our brothers in China in a bag from eBay, fired around 32 volts. Let's move on down here. They are used, here is a list. You have the SMD-B3, 28 to 36. The DB3 is 28 to 36. This is a range. The DB4 is 35 to 45 volts. Most likely you're going to find the DB3, which is the most popular in those lamp dimmers. You can sit here and look at all of the specifications if you want to. Breakover current is in the microamps. But when it breaks over, this does something known as negative resistance. As the current, when this charges up and this breaks over, the current discharges very quickly out of this capacitor, rapidly turning on the Triac, a good clean pulse. And you can read the specs here. You don't want to, okay, the peak current in this thing is 300 milliamps. You don't want to try dumping 10 amps through it. Wouldn't advise it. There's your, you can read that if you wish, and so forth. All right, in this plate, I'm using an MOC 3011 to turn on and off an SCR. Why I'm doing this, these SCR output optocouplers are obsolete. They don't make them. I can't find a replacement. So they're history. But using a diode, make sure this is coming from T2. In this case, it's the anode. You want to come from the anode through the diode, the optocoupler, and the 270 ohm resistor. You can fire the SCR just fine. You may even want to put a Triac in this circuit. You could use the optocoupler, a Triac, and the resistor. I've tried those. They seem to work fine. Okay, here's this circuit again. We talked about that earlier with the back-to-back SCRs. If you're going to use phase control, use a 3010 or a 3020. There's this one again. You can read this again in the spec sheets. All right, noting this here. Your AC at 115 volts, its peak, I usually set it at 120 times 1.414. It's going to produce a peak of about 170 volts. This is rated for 400. Fine. You can use the 3010, which is rated for 250. It will do fine as well. Again, here is your snubbers. If you're using 240 volts, your peak is going to be around 340 volts, and you'll have to use the 400 volt 3020 or the 3041s. And that completes this lecture on Triacs and what to look for. This is Louis Laughlin. I have the links to the individual pages that are related to these projects at www.llaughlin.com. It's been a privilege presenting this to you. I got more coming. Should be SCRs next. Have a great New Year's and a great year.